Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're solving problems that use generalized Hooke's law. In the previous video, we were looking at a biaxially loaded rectangular plate. We were asked to find the maximum in-plane shear strain, which we did in the previous video, and in this video we'll find the volume change. In class, we derived a formula for volume change, and we observed that we can calculate the volume change as the original volume, which I'll call V naught, times the sum of the normal strains. Of course, this assumes that the normal strains are uniform throughout the plate or section for which you're trying to find the volume change. Okay? Now what we want to do is write this equation in terms of our known biaxial stresses, sigma x and sigma y. In order to do that, I've summarized the stress to strain relations for plane stress. So let's start out by observing from these equations we need epsilon x plus epsilon y plus epsilon z. We don't need the shear stress to strain equation in this case. Okay? Epsilon x plus epsilon y plus epsilon z is going to be 1 over e times sigma x minus nu over e times sigma x minus nu over e times sigma x. I can summarize that term right there as 1 minus 2 nu over e times sigma x. Okay? Now, in terms of sigma y, the sum of the three terms is 1 over e minus nu over e minus nu over e times sigma y. Exactly the same thing, plus 1 minus 2 nu over e times sigma y. Okay, so we can simplify this a little bit. Equals the original volume times 1 minus 2 nu over e times sigma x plus sigma y. That's a fairly simple equation based on our known normal strains. The original volume, is the dimensions of the plate, 400 times 550 times 20, and that's going to be, since each is millimeters, that's going to be millimeters cubed. Okay, times 1 minus 2 nu, 1 minus 2 times 0.3 over e, the elastic modulus, 200, and I'm going to convert it to megapascals, 200,000 megapascals, times sigma x plus sigma y, 67 plus a negative 23 megapascals. Those units cancel out. We're left with units in millimeters cubed, which is a volume change, and these numbers compute to 387 millimeters cubed. So that's our volume change. Okay? And relative to the original volume, that seems like a relatively small number. So that's a good sanity check. That concludes this example.